In this video, we're going to look at integration involving inverse trigonometric functions. For the most part, we're going to be looking at integrals that we can solve using integration by substitution, but either the answers or the substitutions that we'll do will involve inverse trigonometric functions. Now, we want to start by looking at some elementary antiderivatives. These are all antiderivatives that we know because we know derivative rules. So for example, we know that the antiderivative of 1 over the square root of 1 minus x squared with respect to x is the inverse sine of x plus a constant. We know that this is true because we know that the derivative with respect to x of inverse sine to the negative 1, x, we know that this is equal to 1 over the square root of 1 minus x squared. So this elementary antiderivative is just the reverse. Instead of looking at the derivative of inverse sine, we look at the antiderivative of 1 over the square root of 1 minus x squared. We also have the second rule, which is the integral of 1 over 1 plus x squared dx is equal to inverse tangent of x plus a constant. Once again, we know this because we have a corresponding derivative rule. The derivative rule is that the derivative with respect to x of inverse tangent of x is equal to 1 over 1 plus x squared. Our third one is the integral of 1 over the absolute value of x times the square root of x squared minus 1 with respect to x. This antiderivative is inverse secant of x plus c. Now this is based on the derivative rule for inverse secant, which isn't as well known as the others, but the derivative of inverse secant of x is equal to 1 over the absolute value of x times the square root of, that's supposed to be a square root, x squared minus 1. One thing that you might notice is that there isn't an antiderivative that results in inverse cosine. That's because of the relationship between inverse sine and inverse cosine. In fact, we have a derivative rule for inverse cosine, which is very similar to the one for inverse sine. In fact, we can write down the rule, the derivative with respect to x of inverse cosine of x with respect to x is equal to the opposite of 1 over the square root of 1 minus x squared. So this is very similar to the rule for the derivative of inverse sine. In fact, you have the same result but with a minus sign. So the corresponding rule for antiderivatives would be the integral of the opposite of 1 over the square root of 1 minus x squared dx is equal to inverse cosine of x plus some constant. Now, in fact, we can take this minus sign and take it out of the integral. So we can write it like the opposite of the integral of 1 over the square root of 1 minus x squared dx is equal to cosine inverse of x plus c. And then what we can do is we can take this minus sign and put it on the other side. Let me just change the color of the pencil. So this becomes the integral of 1 over the square root of 1 minus x squared dx is equal to the opposite of inverse cosine of x plus c. Now if we look at this, let's just circle it here, this one right here, you can see that the integral of 1 over 1 minus x squared dx is equal to the opposite of inverse cosine of x plus a constant. Now we didn't have to do minus c here because this is an arbitrary constant. So when we put the minus sign from the left side to the right side, we only have to put it in front of the inverse cosine. We don't have to put it in front of the c because this c is arbitrary. But you'll notice that this is exactly the same integrand, 1 over the square root of 1 minus x squared, 1 over the square root of 1 minus x squared. So these are the same integrands here that we have there. Now that means that these two antiderivatives are the same, or at least up to a constant. So we have the same integrand, 1 over the square root of 1 minus x squared, And the antiderivative, the general antiderivative, is the inverse sine of x plus a constant. But it's also the opposite of the inverse cosine of x plus a constant. These two functions are the same up to a constant. That is to say, the inverse of sine of x and the opposite of cosine inverse of x are the same up to a constant. They only differ by a constant. So that's why we generally only look at one of the rules. We have an antiderivative rule here for inverse sine, and there is one for inverse cosine, but we don't really need it because they're both the same. They're both antiderivatives for the same function. The other inverse function which is missing is inverse cosecant, and we have the same sort of thing with inverse cosecant and inverse secant that we have with inverse sine and inverse cosine, so I won't write that down. What we want to do now is we want to look at some examples. So let's go on to our first example, example A. This is the integral of 1 over 9 plus x squared dx. If you think back to the antiderivative rules that we just learned, the one that this looks most like is the one that results in an inverse tangent. And in fact, the idea here is we want to use the rule, the integral of 1 over 1 plus, let's say, u squared du is equal to inverse tangent of u plus a constant for whatever choice of u we want for this problem. This is the rule that we want to use. So we want to use this rule. But we can't use it exactly as our integral is written here. We have a 1 over 9 plus x squared, not 1 plus x squared. But that's okay. What we're going to do is we're going to just factor out this 9 right here. Factor out this 9. If you factor it out, then you're going to end up with a 1 there. Well, let's actually do it so that way we can see what's happening. So this is the integral of 1 over, and I'm going to factor out the 9. I'm going to factor it out of the denominator. So we'll have 1 plus, and now we'll be left with an x squared over 9 dx. The next thing that we want to do is take this 9 or 1/9 out of the integral just to get it out of the way. So it's 1 over 9 integral 1 over 1 plus x squared over 9 dx. Now, of course, we have this 9 in the denominator, x squared over 9, because when we factored out the 9, here, we ended up with a 1. 9 times 1 is 9. But then we have to also factor out the 9 out of this x squared term. So that's why there's a 9 in the denominator here. 9 times x squared over 9 is going to give us that x squared. So it might look like we haven't really helped ourselves too much because we now have a 1 here, but this isn't x squared anymore, it's x squared over 9. But that's okay, because what we're really interested in is 1 plus u squared in the denominator for a suitable choice of u. And we're going to be able to rewrite this x squared over 9 as u squared for some u. And this is how we're going to do it. So this is 1 over 9 times the integral of 1 over 1 plus, and x squared over 9 is x over 3 quantity squared dx. And this object right here, x over 3, that's going to be our u. So we're going to let u equal x over 3. Then our du is the derivative, so that's going to be 1/3 dx. Now we don't have a 1/3 dx, we have a dx, but we can just stick in a 1/3 here like this. But of course, if you multiply by 1/3, you also have to divide by 1/3 or multiply by 3. So let's just put in a times 3 over here like that. Now we can get away with this because 3 times 1/3 is 1, so we're not actually changing the value of the integral. And you can multiply inside and outside like this because 3 is constant, so you can multiply by 3 and divide by 3. Okay, well, if we do all of this, then, I mean, what's the point? Well, this 1/3 dx, that becomes our du, And this integrand right here, 1 over 1 plus the quantity x plus 3, that quantity squared, becomes 1 over 1 plus u squared. And now we have exactly the form that we're looking for. So let's change back to blue. So what do we have here? We have 1 over 9 times 3, that's 1/3. So we have 1/3 times the integral of 1 over 1 plus u squared du. Okay, now this we can integrate. This is one of our elementary antiderivatives from the previous slide. So this is 1/3 times the inverse tangent of u plus a constant. So this is just this rule that we're using right here. Okay, so this is our answer, but of course it's in terms of u. We need to get it back in terms of x, but u is equal to x over 3. So we're just going to take this u equals x over 3 and just plug it back right in right there. And that's going to give us 1/3 inverse tangent of x over 3 plus a constant. And that's our answer right there. Okay, let's do another example. Here we have the integral of 1 over the square root of 25 minus 4x squared. So what rule does this look like? We want, in order to figure out what antiderivative rule we're going to use after a substitution, we need to look at this integrand and ask ourselves, what does it look most like? Out of those 3 elementary antiderivatives we had at the start, which one does this look most like? And we have a constant minus 4 times x squared. So the rule that we want to use, and again, I'm going to phrase it in terms of the variable u, because after the substitution, our integrand will have u in it instead of x. So the rule we want to use is the inverse sine rule. So it's the integral of 1 over the square root of 1 minus u squared du is equal to inverse sine of u plus a constant. Okay, so this is the rule that we want to use right here. And we have to figure out what u is in order to make this expression, 1 over the square root of 25 minus 4x squared, look like 1 over the square root of 1 minus u squared. Well, the first thing to do is to get rid of this 25. See, we have a 1 here, so we want to have a 1 in this expression too. So we're going to do what we did before, which is factor out the 25. So this is going to look like the integral of 1 over the square root, and I'm going to factor out that 25, and we're going to end up with 1 minus 4 over 25 x squared. And all of that's underneath the radical, like so, dx. Okay? Now this 25 is underneath the radical, and the square root of 25 is 5. So this equals the integral of 1 over 5, like so. And now we're going to have a fraction with 1 in the numerator, and the bottom is going to have a square root, and the thing underneath the radical is 1 minus 4 over 25 x squared dx. Okay? Now the first thing I can do is I can take out this 1/5. So I'm going to write this as equals 1 over 5 times the integral of 1 over the square root of 1 minus. I want to make this term here look like u squared. Now notice that 4 over 25 x squared is the same as 2 over 5 times x quantity squared dx. So here I do have something squared, 2 over 5x quantity squared. So what I'm going to do is I'm going to let this term right here, I want to let that be my u. That's the thing that I'm squaring. So I'm going to let u equal 2 over 5 times x, and then du is the derivative, so that's just going to be 2 over 5 dx. So once again, I need to put a 2 over 5 here. But 2 over 5 is a constant, so I can just multiply by 2 over 5. And if I multiply by 2 over 5, I have to divide by 2 over 5. But dividing by a fraction is the same as multiplying by the reciprocal. So this is the same as multiplying by 5 halves. So let's just put a 5 halves in front there. Okay, well if we do that, then we now have 2 over 5 dx, which is our du. And the rest of our integrand here, is 1 over the square root of 1 minus u squared. And what do we have out front? Well, we have 1/5 times 5 halves. So we can cancel that 5 with that 5. And what do we end up with? This is equal to 1 over 2 times the integral of 1 over the square root of 1 minus u squared du. And this is the integral that we were looking for, the integral of 1 over the square root of 1 minus u squared. And we have a rule for that. That's the inverse sine rule. So this is just going to equal the 1/2 in front times inverse sine of u plus a constant of integration. But of course, u is equal to 2/5 x, 2 over 5 times x. So this right here will go right into here. And what are we left with? This will leave us with 1/2 inverse sine of u, but u is 2 over 5 times x plus a constant. And there's our answer. Okay, let's do another example. So this is example C. This one looks quite messy. It's the integral of e to the x divided by this expression, e to the x times the square root of e to the 2x minus 1. Okay, well, this is a little bit more involved. And we're going to make use of a substitution. And the substitution we're going to make will involve an e to the x. In particular, let's look at this e to the 2x right here. Well, what we need to know for this, we need to observe that e to the 2x is equal to e to the x quantity squared. So that's the basic idea here. What we're going to end up doing is letting u be equal to e to the x, so that e to the 2x is equal to e to the x squared is u squared. So that's the basic idea. So this term right here is going to be u squared. And this e to the x is going to be u. Okay, well, what about this other e to the x? Well, this actually comes into play with the du. So if u is equal to e to the x, then du is equal to e to the x dx. So this e to the x in the numerator, we're going to group that together. So we're going to take this e to the x and group it up with that dx, and that's going to give us our du. So let's rewrite this. So we're going to have the integral of, let's write it as 1 over e to the x, again, times the square root of e to the 2x minus 1 times e to the x dx. Okay, so let's just change the color. This e to the x dx, that's going to be our du. And this term right here, everything else in the integrand, is going to be 1 over u times the square root of u squared minus 1. So what we have here is this integral, after we do the substitution, is equal to the integral, and let's put an equal sign there. This is equal to the integral of 1 over u times the square root of u squared minus 1 du. Now this should look somewhat familiar. This looks like one of our rules, one of our elementary antiderivatives. So the rule we want to use is the integral of 1 over the absolute value of u times the square root of u squared minus 1 du is equal to the inverse secant. So this is going to be secant inverse u plus a constant. So this is the rule that we want to use right here. Now, what we have is very similar. but you'll notice in our rule we have an absolute value of u, and over here we just have a u, but that's actually fine because u is equal to e to the x. So let's just change this back. Note u is equal to e to the x, but e to the x is always positive. It's never 0 or negative. U is always positive. So what that means is that u is equal to the absolute value of u. It's always positive. So in fact, we can put absolute values around that u. And now we can apply this inverse secant rule directly, and that's going to give us inverse secant of u plus a constant. But what is u? This u right here is, of course, e to the x. So we just plug in u equals e to the x. And this gives us inverse secant of e to the x plus a constant. And that is, in fact, our answer. Now, one thing that you might notice, if you look back at our original integrand, notice that this isn't in simplified form. There's an e to the x in the numerator, but there's also an e to the x in the denominator. We could cancel those out, and that gives us a simpler integrand. So let's write this as a note, or as a remark. Let's just say remark. So if we reduce this expression, so we cancel the e to the x in the numerator with the one in the denominator, we're just going to have the integral. Let's fix that integral symbol. And so it's just going to be 1 over the square root of e to the 2x minus 1 dx is equal to inverse secant e to the x plus a constant. These are actually the same thing. It's just that here the integrand is simplified. Okay. Let's move on to our next example. Example D. The integral of 1 over something kind of complicated, x plus x times ln of x quantity squared. Now when we write ln of x quantity squared like this, let me just write this again as a little note. Note, when we write ln of x squared like that, what we really mean is ln of x quantity squared like that. Okay. So we just didn't write the brackets here just to make it look a little nicer, but that's what we really mean. Okay, so this integral, let's just rewrite it. So this is the integral of 1 over x plus x times ln of x quantity squared dx. Okay, so what are we going to do here? Well, we want to make this look like one of the elementary antiderivatives that we started with. And it might not really look like any of them at the moment, but notice we can factor out an x in the denominator. Let's do that. So this is going to be the integral of, and I'm going to write this as 1 over x times 1 over 1 plus ln of x quantity squared, like that, dx. Okay, so all I've done here, let me just fix my 2, like that. Now, notice what I've done here is I've just factored out that x. So x is in the denominator here. So x times 1 is x, and x times ln of x quantity squared is that term right there. Okay, what I want to do is I want to take this 1 over x, and I want to put it next to the dx, just for fun. Let's do that. So this is going to be the integral of 1 over 1 plus ln of x quantity squared times 1 over x dx. Okay, so let's ask ourselves, what rule does this look like now, if anything? Well, the key is this term right here, 1 over 1 plus something squared. So the rule that we want to use, is we want to use the inverse tangent rule. So it's the integral of 1 over 1 plus, and I'll write it as u squared, du, is inverse tangent of u plus a constant. Now we just need to figure out what u is in order to make this true. Well, the idea presents itself because we've got something squared right here. So what we're going to do is we're going to let u be equal to the thing that we're squaring. the thing that we're squaring is ln of x. So we're going to let that be equal to our u. So what is du? It's the derivative. Derivative of ln of x is 1 over x, and then dx. And then we go, oh wait, that's convenient. There's a 1 over x dx right here. Okay, so this 1 over x dx right there, that's our du. And everything else right here, this is 1 over 1 plus u squared. So right away, we have a familiar looking integral. It's the integral of 1 over 1 plus u squared du. And now we can apply our rule that we have right here, our inverse tangent rule. So it's tangent inverse u plus a constant. But of course, u, that u right there, is equal to ln of x. So what we're going to do is we're going to just take this and plug it right in there. And that's going to give us inverse tangent of u is ln of x plus a constant. And that's our answer. Well, let's fix our c a little bit. So there's our answer. All right. Inverse tangent of ln of x plus a constant. Let's do another example. Example E. The integral of x over 1 plus x to the 4th dx. Well, this kind of looks like our inverse tangent antiderivative. Let's just remind ourselves of the rule again. So our rule that we're thinking about using here is the integral of 1 over 1 plus u squared du equals inverse tangent of u plus a constant. So this is the rule that we're going to use here. Now, the integral that we have isn't exactly like that, but notice in the denominator we have 1 plus x to the 4th. Well, of course, x to the 4th is not the same as x squared, but it is a square. X to the 4th is x squared quantity squared. So what I'm going to do is I'm going to rewrite this. I'm going to rewrite this as the integral of 1 over 1 plus, and instead of writing x to the 4th, I'm going to write x squared quantity squared times, well, notice I didn't write the x in the numerator. I'm going to write it off to the side, x dx. And why am I doing that? Because I have something here that's 1 over 1 plus something squared, right? My integrand, at least part of my integrand, is 1 over 1 plus something squared. So I'm going to let the u be the thing that I'm squaring here. So u is going to be equal to x squared. Well, if u is x squared, then du is the derivative, which is 2x dx. And here we have x dx, x dx. The thing that we're missing is the 2, but this is a similar thing that we've seen before. If you're lacking a constant, you just multiply by that constant. So I'm just going to multiply by 2. But of course, if you multiply by 2, you have to divide by 2. So I'm going to just divide by 2 like that. And what's left over? Well, what do I have now? Well, this 2x dx, that's du. And everything else is 1 over 1 plus u squared. So now, if I just rewrite this, I'm going to have 1/2 times the integral of 1 over 1 plus u squared du. And this is exactly the integral that I wanted. So I can use my inverse tangent rule, and this will become 1/2 inverse tangent of u plus a constant of integration. But what is u? U is x squared. There's my u right there. So again, I'm just going to take this and just plug it in right there. And what does that give us? That gives us 1/2 inverse tangent of u, but u is x squared, plus a constant. And that's our answer. All right, let's do one more example. So here we have a complicated looking integral, the integral of inverse sine of x divided by the square root of 1 minus x squared dx. So this might look a little bit different, and it is different, because now the inverse sine isn't part of our antiderivative exactly, it's part of our integrand, it's inside the integral. And we want to use a substitution, and the substitution we're going to use actually is this inverse sine. Let me rewrite my integral so it looks a little bit more convenient for using a substitution. So I'm going to rewrite this as the integral of inverse sine of x, like that, times 1 over the square root of 1 minus x squared, and all of this is times dx, or, well, all of this has a dx at the end. All right, well, let's take a look at it. All I did was I took this inverse sine of x, and I just wrote it out to the left, and I multiplied by 1 over the square root of 1 minus x squared. So the thing in the denominator is still in the denominator, but it's got a 1 in the numerator instead. Now, the reason I did this is if I let u be sine inverse, then what is du? Well, it's exactly everything that's left over, du, right? So if u is inverse sine of x, then du is 1 over the square root of 1 minus x squared dx, which is exactly what we have here. So now we just have the integral of u du. And now this is an elementary antiderivative, so this is going to be u squared over 2, just using the power rule, plus c. But what is u? U is inverse sine of x. So this is going to be equal to inverse sine of x. I'm going to square that over 2, and then it's plus a constant of integration. And that's our answer.